So hi everyone, welcome to week 7 of Techquitable. For today's lesson, we'll be going over trees and graphs. And
good morning.
Yep, you guys want to move on to the next slide and start with the introduction. Alrighty.
Okay, so hi everybody. My name is Jaren Colbert, also usually mispronounced as Jareen Colbert, but I'm not that fancy. I'm a software engineer at Greenhouse, where I've been for about 2 years, and I went to University of Maryland College Park, graduated in 2010.
Cool, I'll be your other instructor for the day. My name is Joyce. I work at Chime, which is an online neobank. I'm from Canada originally. I graduated from Toronto in 2019. I moved to the Bay Area, and previously I was at Google.
Okay, so today I'm going to cover trees and binary trees. Joyce is going to take over for graphs. We've got some sample problems for you all to work through as well. All right, so most graph and tree problems boil down to either how do I get this information, like how do I recognize that this problem is a tree or a graph problem? How do I get my data into that format? And then how do I do different operations? And what are the operations on a tree structure or a graph structure? And so traversal is going to be a big part of what we cover today. How do you, once you have a graph structure already defined, how do you move through it and visit every node within that structure? And, you know, compared to some of the other data structures that I know you all have reviewed so far, traversal and doing different operations on a tree, not just traversal, but even insertion, searching, deletion, things like that can be trickier for trees and graphs compared to the other structures that you reviewed. So it's really key here to practice and work through some of these problems on your own. We have a lot of ground to cover today. So we have a few examples, but please, especially for this topic, I'm going to encourage you to do some of these as practice problems on your own. All right, so what are trees and how do we compare them to graphs? All trees are graphs, but not all graphs are trees. Trees are just a certain restricted type of graph. And graphs are just an interconnected set of nodes, or sometimes called vertices, and edges, which are the connections between those nodes. So a tree is just a set of nodes where the nodes have references to their child nodes, and only the parent nodes can be aware of those child nodes. Whereas graphs, we have this concept of adjacency instead, where you just have a list of nodes that each node is connected to. So a tree is a graph, just a specific type of graph. And even within trees, we'll get into specific types of trees here. And I hope you all know, please interrupt me if I'm moving too fast. Please ask any questions as you can, and I'll try to monitor the chat as well. Okay. So to introduce trees, a tree is a data structure that basically represents information in a hierarchy. So node A is the root of our tree, and each of its children are sort of thought of as sub-information to the node A. So B, C, and D are related to A, but at a different hierarchical level than A. So some examples that are kind of easy to think about. This is a set of Reddit comments, but this is a parent comment. These are 2 child comments, and each comment is sort of a reply to a parent comment. So this comment has this comment as a child, and you can traverse down to see all the related comments for a parent. Likewise, an HTML document is a really good example of a tree structure. The root of an HTML document is the HTML node, and each node within that XML or HTML document can be thought of as related to its parent. The head and body sub-elements are children nodes of HTML. Likewise, the list items are children of an unordered list. So we've covered some of this so far, but in this tree structure here, a node is similar to a linked list node. I know you all covered linked lists, but this node has some data. It could be, you know, any sort of data that we're representing, but each node has a data object as well as a pointer to one or more child nodes. And so each child, B, only has one parent. B has its parent of A, C has its parent of A, and D has its parent of B. And depending on what type of tree we have, each node can have any number of children. So in this, we have A has 2 child nodes of B and C, B has 1 child node of D. And sometimes the definition and restrictions of the type of tree will dictate how many children, how many child nodes each parent can have. Tree data structures grow down. So A is the root and it gets larger as we move down the tree. This tree has 3 levels, starting with A, level 2 is, counting from zeros is level 0, level 1, and level 2. And leaf nodes are nodes without any children. So the leaves of this tree are D and C. Does that make sense so far? All right, and to continue our terminology, a lot of sample problems that you may see could involve getting all the nodes at one level, which is an example we'll go through a little bit later, traversing every node within a tree, or getting the height of our tree. So, or the depth, also called the depth of our tree. So if the node 1 is at depth 0, 2 and 3 are at depth 1 or level 1, and 4, 5, 6, and 7 are at 2, and likewise. So the height is the maximum depth of any node in the tree, and we'll cover subtrees in a second, but even within some of those subtrees, you can see what the height of the subtree is as well. So let me go back. Can someone tell me what the height of the subtree starting with node 2 is?
I think that would be 3.
Yes, so the subtree starting at 2 has 2 levels of children. So it's actually 2. The height of the subtree starting with 2 is 2. The height of the entire tree is 3. Does that make sense? So if 2 if we're starting with node 2, that is level 0 for that subtree. Levels 4 and 5 are 1 level deep from that parent node, and nodes 8, 9, 10, and 11 are 2 levels deep. Okay, can someone tell me the height of the subtree starting with node 13?
Is that 0?
It's sort of tricky, but it's 0. So yes, it doesn't have any subtrees, it doesn't have any children. It is a leaf node. So yes, it has 0 height or depth. All right. So representing a tree in code, and hopefully this class looks a little bit familiar to us. It's similar to the nodes for linked lists as well. So each node object has a concept of some data that it's carrying, and then an array or a set of children. So here our root node is starting on this line with node of A, and so we're instantiating it with A as its data. One thing here to recognize as we sort of step through this code is that we're creating all of our nodes up front, and then we're adding children to them as we traverse, through creating our data structure. So we start by just creating the nodes independently, A, B, C, then D in our first 4 lines. And then the next 3 lines are adding the child nodes, adding those relationships to each node. So we're saying for node A, add the child B, node A, add the child C, node B, add child D, and then we're traversing here of seeing what those child nodes are. And since we're using an array structure here, the implementation of adding child is just appending that child node to the children list. Is that clear so far? Could someone tell me what the benefit or difference might be if we used a set for our child to represent our children nodes as opposed to an array? Would there be any benefits, any downsides, any trade-offs?
I was thinking if they have the same value, maybe there'll only be one instead of two being recorded there, but I'm not sure.
Right, that's a good point, is that if we use the set, we'd have to assume each node is unique. That a set there, you couldn't have two children with the same data because they sort of get collided in that set. Very good point. Okay. All right, so any questions before we move on to specific types of trees? Any questions
Yeah.
here on this implementation?
Yeah, can we go back one slide? Yeah, here I see that depth and height sort of follow the same definition, but I thought that they were opposites. So if I go to the first node, the height would be 3, but the depth will be 0. But here I see something different because height and depth are the same when I look at the bottom.
So I see what you're saying. So the height of this entire tree is 3. And I think that's sort of counting from the root node of 1. Whereas from the root node of 1, the depth here is 0, but then on level 1, which is nodes 2 and 3, that is a depth of 1, but the height of that tree is 2. So you're right, you're absolutely right that the depth and the height are sort of inverse or opposites of each other. But is it, I'm trying to look at the notes here. Is that confused? Is there something confusing of how we're labeling
the part
that?
that was confusing me was when I was looking at the very bottom, I see the height is 3 and then I see that depth is 3. So I thought that they were, I thought that your diagram was trying to imply that they were the same, but I was like, no, but that's opposite. That's all.
Okay, yes, no, you're absolutely right. And sorry that the labeling is confusing.
Yep, thank you. That makes sense.
Any other questions here or in the slides that we've reviewed so far?
Wait, on that question, I was wondering, so the height will not include the leaf nodes, will not include the level of leaf nodes?
It is, so it's the height of our, so we kind of don't count the level that we're on. So we count the level of the subtrees. So here the height is, we're at depth 0, 1, 2, 3. So the leaf nodes have a height of 0. This is a height of 1, a height of 2, a height of 3. Hopefully you can see my cursor, correct? Okay. Okay, very good question so far though. Okay, I'm going to move on to binary trees. Okay, so as we've covered already, a tree can have any number of children, and we saw that in our implementation here, that there's no limit, it's just an array representing any number of children that this individual node may have. So in this tree, the root has 3 children, its first child has 3 children, but then its second child has 1, and its third child has 2 children. So in a general tree structure, any node can have any number of children. What we'll commonly see for specific implementations of trees are binary trees. So the definition of a binary tree is that each node can have no more than 2 children. So with this node here, it has no children. So leaf nodes will be at the end of our tree there and will have no children. And any of the nodes within our tree could have 1 as well. But a binary tree node can have no more than a maximum of 2 children. Okay, so in code, we still have the same data structure here where a node has a data object and some list of children. And we could even add some validation here to say, hey, if you try to add child and the count of children is already 2, to throw an error or something like that. But the implementation is generally the same. And so one additional change to binary trees is that in contrast to having any number of children here, we generally think of our 2 children as a left half and a right half. And we'll see some applications of why we think of them that way. But for our binary tree interface, if we go back to our picture, we think of this branch as being our left branch and this child as being our right child. Again, left and right of this parent. And similarly to our previous example, we instantiate our nodes. We have our instantiating 1 as our root, 2 is our left node, and 3 is as the right node of that root parent. And we set root.left to our left node and root.right to our right node. So this is instantiating a tree of what height? Can anyone tell me how high this tree would be? So it has a root node, 1 left node, 1 right node.
Height of 2.
So it would be sort of this subtree here.
Mm.
And so a height of 1.
Okay.
Okay. All right, so we've talked a lot about what trees are. And as trees are specific types of graph, binary trees are specific types of trees, and they're useful for particular types of problems. So an additional constraint on a binary tree is the implementation of a binary search tree. So let's go back to our visualization here. Within a binary search tree, it is a further restriction where it is a binary tree, so each node has at most 2 children. One additional restriction on a binary tree is that all of the left nodes of that tree have to have lower values than their parent. So left is lower, right is higher for every subtree of that binary search tree. And one implementation of that makes searching really easy. Certain implementations of map data structures or hash map data structures for lookup, some implementation of sets use BSTs under the hood for easy and efficient searching. Similarly, heaps are a specific type of binary tree where they are self-balancing and they make it very easy to see the highest number or the lowest number of a set of data. So usually it's the highest number, but sometimes it can be the lowest number. You can represent arithmetic operations as a syntax tree. So where every operation is a node in the tree and we're traversing and sort of doing 1 + 1 or 2 - 3, we can represent those. So some calculator implementations are represented as syntax trees. And then a Huffman tree is used for data compression. Alrighty, so keep going. And another piece of terminology for trees is the concept of being balanced. So that means that the left and right subtree heights differ by at most 1. So it's a complicated way of saying that balanced trees you cannot fill up a sublevel of a child before you fill up the siblings. So this left tree is balanced because the difference between the height here is 2, so 1, 2, and the heights of the right subtree and the left subtree just differ by 1. So there is the height here is the height of this subtree is 0, the height of this subtree is 1. So the difference of those 2 heights is 1. They differ by at most 1, so they differ by 1. Here, that's not the case, where the height of this subtree is 2, because from 1, we have 1, 2, 3. And the height here is just, there's no additional height, so it's 0. And so they differ by 2 levels as opposed to 1. Does that make sense? So we have an unbalanced tree here. And as the trees get more unbalanced, our tree operations, including traversal, insertion, and search, get to be even more expensive and complicated. So we want to make one application of trees, as you'll see, is balancing them, making sure that trees are balanced. Okay, so our binary search tree implementation. For every node, values in the left subtrees are always less than the values of the root node. So all left subtrees are low, right subtrees are high. And then the additional constraint is that for every subtree, the left subtree and the right subtree must also be a binary search tree. So that constraint of the less left and right high have to be true for every subtree within that tree as well. So the time complexity for searching here is log n. Can anyone tell me, and which I think is a little bit tricky, can anyone tell me why they believe the searching might be log n? Dario, looks like you're raising your hand.
I was thinking that at no point would you ever have to visit every single node, because you could say I'm looking for 4 and I'm starting at 8. Because 4 is less than 8, I know that it has to be on the left side, so I go there. Now 4 is greater than 3, I know that it has to be on the right side, and so on and so forth. I'll never have to visit every single node, and that's why.
That's exactly right. That's exactly right. Very good. And the reason why it's log n, so it's the opposite of exponential growth, right? We're halving by an order of magnitude every time. And like you said, because we know we have certain assumptions about how this tree is organized, we're always sort of counting out half of, or at an optimal case, half of our nodes here. So like you said, we're throwing away this side of the tree because we know that 4 is less than 8. We're counting out this whole half of the tree because we know 4 is greater than 3. And so each time we're counting out about half of, we're dividing by 2 the search space that we're looking for. So if we were to write this out, it would be O of log base 2 of n. But I think as we've covered in some of our time complexity, we would drop that 2, log 2 of n, log 3 of n, doesn't really matter. It's log of n. The base doesn't matter here. Each step down the tree halves the number of elements in our search. And this is this picture is an example of a tree where this node of 2 violates the constraint of the binary search tree. This node is, although it is not a direct child of node 3, it is still on the right. It is a child of the right half. The right half of the 3 node. So every node that is to the right of 3 has to be greater than 3, and 2 violates that. Yes, Dario.
Could a binary search tree ever be self-balancing without breaking any of the rules?
Yes, some implementations of binary search trees are self-balancing, where insertions, and I'm trying to think of an example, but where insertion, to maintain this tree as balanced, insertion has to move those things around. You can't just insert a node anywhere and still maintain it to be a BST. So the insertion algorithms have to account for rebalancing the tree. That's a really good question.
Okay, that
Yes.
makes sense. So I'm thinking about like a bubble or a bubble up or bubble down, where you would place it somewhere and then just move it around. So like a linear insertion time.
But right, so if this was a general tree implementation, then you could have a near linear tree where each of the child nodes just has one, each node has just one child, and we're kind of looking in a line as opposed to having our search space as we do in BSTs. But because BSTs have to stay balanced and have to stay, insertion cannot be random, right? We have to insert in the correct place to maintain the BST's order, so that searching, so that the entire point is so that if this thing is balanced and constructed correctly, that is the only way that this search becomes log of n.
That makes sense. Thank you.
Mm-hmm. Any other questions here? Okay. All right. And then, so we have 4 traversal methods for trees. We're going to go into BFS in depth, and then we'll do sort of a pseudocode implementation of depth first search. So breadth first search, or also called level order traversal, hits every node in the tree one level at a time. So that is a short way of saying all of the siblings of a node are processed before any of those siblings' children. Dario, I still see your hand up. Are you still, you have a question here?
I'm sorry, no, I forgot to lower my hand, sorry.
No worries. I just wanted to make sure. Okay, so if this is our tree here, level order traversal will traverse the tree starting at the root node, which is 1, hit its first child, which is 2. And before moving on to any of 2's children, we have to process its sibling first. So we'd move on to 3. Once all of the nodes at one particular level are processed, printed out, then we start with the next level. So then 4, 5, 6, and 7 before moving on to anything at the next level. So breadth means let's go wide before we go deep. Let's go to siblings before we go to children. And our last row there would be 8, 9, and 10. So our output would be in order of, our countable order: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, question for you all. If we are starting with breadth first search, we go from 1 to 2 to 3. But in our implementation of our nodes, the only way to get from a node is through its children. Like the only way to get to 4 is through its parent of 2. So how do we make this leap from 1 to 2 to 3? And once we're at 3, how do we get to 4?
I think we're going to use a queue, right?
Absolutely, yes. So I think we have a little hint here, but if we use a queue to keep track of each node, the nodes at each particular level's children, then we just add them to the queue to be processed later while moving on to the sibling node. And that queue will maintain the ordering so that these children will be processed before 3's children, but 3 will still be processed before any of the children at this level. Okay. So this is an implementation of BFS. To just step through this. So our base case is if root is empty, we're just going to return. And we're using a double-ended queue here, a DEC data structure as our queue, creating an empty queue and adding our root node to it. And then we're just going to loop through the items in our queue until it's empty. We start, because we have one item in our queue, our root, we use pop left to get that node. We process it by printing it out, getting its key or its value or its data. And then if it has any values for a left child, append that to the queue. If it has a value for right child, append that to the queue. We would continue to loop here. And so for this implementation, we'd start with root, add 2 and 3. Then 2 would be at the top of our queue, pop that off, add its children, 4 and 5, but the next thing in the queue would be 3. We'd add its children, 6 and 7, and once we pop off the queue again, we're starting back at 4. So that queue data structure, I think it was Jiyoung, I hope I'm pronouncing your name correctly, that said we would be using a queue here. Absolutely right, to keep track of those children. So very quickly, the last traversal methods here are depth first search. And when Joyce goes into graphs, she's going to give a more deep example of this. So we're just going to talk about this in a pseudocode level. But the difference between the DFS mechanisms, the only difference here are when you visit the node that visit your root node. So in order means you visit the left subtree, you visit your root node, and then you visit the right subtree for every node in our tree. So we start, as always, with our root node of 1. Go back. Start with our root node of 1, traverse its left subtree. For this subtree, we visit its left subtree, we get to 8, but 8 doesn't have any left subtrees, so we finally visit that node, adding that to our output. We backtrack and visit 4 because it doesn't have a right subtree, and we have 4 to our output. We backtrack and visit 2 because we're visiting that node after it's left, but before it's right. We add 5 to our output. Now that all of one's left subtree is fully processed, we then add 1, starting now with its right subtree. We go all the way down to the left subtree of 9, just like we went all the way down to the left subtree of 8 here. So 9, then 6, then 10. Now that we've processed all of 3's left subtree, we hit 3 and then 7 for our final 2 cases. And this is our result here. 8, 4, 2, 5, then back up to 1, but then jumping down into the left subtree here, 9, 6, 10, 3, 7. For our example of pre-order, I think I jumped ahead here. The only difference here is that we're visiting our root node first, then traversing left, then traversing right. So can someone walk me through what our output might be? Get us started with visiting the root node first. Then we traverse down the left subtree before coming down to the right. So we visit each node first, starting with 2. Oh, click. Then 4, then 8. And since we've processed all of the left subtrees and this one, we start with right. Then because we visited the root node and its left subtree, now we go back to its right, visit this root node of 3, traverse its left subtree. 6, visit this root node now of this subtree and its left subtree, to 9, then to 10, then to 7. And our last one is exactly the same pseudocode, just visiting the root node last. So that's the only difference between in order, post order, and pre-order traversal is when you visit this root node. And lastly, we're going to traverse all the way down to the left subtree, then the right subtree before visiting the node itself. So left, this doesn't have any right. We're visiting the right subtree of this root node 2 before visiting 2. 2 would get processed. Next. Why are my clickies not working? There we go. A little bit delayed. So 2, and then we traverse all the way to the left of this subtree, 9, then 10, back up to its parent, 6, but then the right subtree of 3 first before we're going back up to 3, and then 1 is last here. Okay, so I would encourage, especially for the last 3 where we just went over these in pseudocode, to try to type up your own implementation for these. And they should be very similar, just when visiting the root node is different. With that, where are my clickies? Okay, also good things to practice. Traversing your tree with any of these algorithms, finding the height and your depth of the tree, getting all the nodes at one depth, so that's our BFS implementation. Determining if a tree is balanced, determining if a tree is a binary search tree or not. And then we have some links here once you all get the slides to some additional resources for tree traversal, different types of binary search trees, and some additional tree problems here. And with that, I will turn it over to Joyce.
Awesome, cool. Before we move on, did anyone have any questions about any of the tree stuff we just covered? Going once, going twice. All right, on to graphs then. Can anyone remind me the difference between a tree and a graph? Yeah, Dario.
Oh, go ahead, Dario.
Sorry about that.
You can
Dario
go,
had his
go.
hand up.
No, you can go, it's all good.
A tree is hierarchical.
Okay, can a graph also be hierarchical?
Yeah, I think, yeah, so all trees are graphs, but not all graphs are trees, so.
Yeah, good. Yeah, I think that's the key thing. So all trees are graphs. So whatever definition you give me for a tree, that will also define a graph. One thing I want to highlight, what's the relationship in a tree between the number of nodes and number of edges. So which one would be bigger, or will there be more nodes or more edges in a tree?
There'll be more nodes.
Yeah. Jaren, do you mind navigating to a slide where we can look at a picture of a tree real quick? If we go up, maybe. Yeah. So you'll notice in every tree, there will always be one more node than the number of edges, because every node basically has one parent exactly. So this is like a key feature that's the difference between trees and graphs. So graphs can have a lot more edges because you can have edges that point to itself, nodes that point to itself, or nodes that have multiple parents, essentially. Does that make sense?
Yes.
Okay, cool. I'll come back to why this is important later, but let's move on for now. So next slide, please.
Okay, Joyce, did you still want me to drive, or did you want to take over?
I can share. Okay, all right. So key difference is how graphs can have a lot more edges than trees, and graphs are generally used to represent connections between data. So a very typical example of a use case for a graph is Google Maps. So on Google Maps, I'm trying to find the distance between two different places. We can imagine each place is a node in my graph, and the edges are the roads between places, and each edge is given a weight. So I just have to find the shortest path between the 2 points, and that's basically what Google Maps is doing. So this is an example of a graph where each edge has a weight. So for example, here from start to location A, it takes 5 units of, let's say, time, but to B, it takes 2, and then from B to A, it takes 8. So there's 2 options to get to A. I can go directly, or I can go through B, and obviously going directly is faster. There's also graphs where all the edges are unweighted. So you can say all edges have equal weights. Can anyone think of an application of a graph that might look like that? What like real world model might a graph be used for where the edges are unweighted?
Maybe if we represent like a company, the employees, so we will represent like manager and employees relationship, in which case I think that would work.
Yeah, that's a great example. So the edges there would definitely be unweighted. But I think in that example, it would actually be better to be represented as a tree, because you just have one manager that has several reports, and every report usually has one manager only.
I was thinking about McDonald's when you have like a lot of different stores.
Yeah, that works too. Yeah, good one. Another common one is Facebook. If you think about Facebook friends and how they're related, each friend can be a node, and you have edges if you're connected as friends. That would also be an example of an unweighted graph. Cool. So let's go through a few different types of graphs. So very similar to trees, we have nodes, we have edges. Nodes are also called vertices, but graphs generally have more distinctions. So we talked about weighted and unweighted already. We also have graphs that can be undirected or directed. So undirected is also called bidirectional. So that means from one node, you can go both ways, traveling an edge to visit the node that you started on. Directed means edges basically have an arrow to them, so you can only go one way that the arrow is pointing. Another distinction we have is cyclic and acyclic. So a cyclic graph means you can, starting from one node, reach the same node again. So here we can go through this triangle, and we'll get back to the node we started on. In an acyclic graph, this is impossible. So starting from the top node, I can traverse downwards, but there's no way to get back up to the top node here. And then the last distinction we have is sparse versus dense graphs. So sparse graphs means there's not a lot of edges. So for trees, they're generally a type of sparse graph because trees don't have a lot of edges. And dense graphs, this means there's a lot of edges connecting your nodes. Okay, so we can represent graphs in code in a few different ways. I know this is a lot of text, so let's just focus on the image at the bottom here. One key way is to represent a graph using a 2D array of Boolean values, where you can say false represents that there's no path between two nodes, and true represents that there is a path between two nodes. So in my sample graph here, there's no path from A back to A. So in my 2D array, in the indices that represent A is 0, meaning false. But A can go to B, it can go to C, and it can go to D. That's why all of the B, C, D values are true. And there's no way for it to go to E, which is why that's false. Does anyone have questions about that? All right, so the code here is a little non-trivial to understand, but basically what I'm trying to do here is I'm going to say we're going to initiate a graph with a number of vertices, so let's say 5. And the first thing I'm going to do is I'm going to create a 2D array that's all false. That's 5 by 5. And then whenever I add an edge, I'm going to say I add bidirectional edges. So I'm going to add an edge that goes both ways. So A can go to B and B can go back to A. As we can see here, A can go to B and B can also go back to A. Those are set to true. Does that make sense? No questions? Okay, cool. So traversal algorithms is very similar to trees behind BFS and DFS, but the runtime here is a bit different. Does anyone remember what the runtime we said for trees was for BFS and DFS?
Well, for breadth first search in the tree, you have to visit every node, and if you let node equals to n, then it will be linear.
Yeah, it'll be O of n, exactly. Yeah. But here, let's say a node is a vertice, what we call V here. So why is this not just O of V? Why do we have this extra thing we have to add to our runtime? Why do we have to add E to it?
What if you have like a bi-directional? So you have to visit, the edge also matters.
Yeah, or you can have a very dense graph where you have a lot of edges. So remember at the beginning, I said that in a tree, you always have more nodes than edges. Edges is always one less than your node. So you can think of the runtime for a tree is also just nodes and edges. But since the edges is a smaller factor, it would be like saying it was O of 2 times the number of nodes, which is just O of n. But here, since we can't rely that there's less edges, we have to account for the fact that we might traverse every single edge once when we're going through our tree. Okay, so let's look at BFS really quickly. So again, I'll start with the image. So assuming that we start at the node number 2, the first nodes we would visit are the ones closest to it. So we visit 1 and 3. And then from there, we would visit 4 because it's furthest away from our initial starting node. And we do this very similar to how you would traverse through a tree. You would again use a queue. So I would initialize my source node to be the only thing in my queue. And then I would loop through my queue until it's empty. So while it's not empty, I see what was the last thing I visited, which was the 2. And then I add all its neighbors to my queue. So from 2, I would add 1 and 3. And then I would visit the next neighbor in my queue. Let's say it's a 1, add the neighbor, which is 4. And then I've been to all my nodes that I have in my graph. For DFS, again, in the same graph, if we start at 2, the difference here is instead of visiting the closest neighbors, would pick one closest neighbor. So here I picked 1, I would visit 1. And then from that point on, I would pick the closest neighbor of 1. So here I pick 4, I visit 4, and then I pick the closest neighbor of 4, which would be 3. And this would continue until I have no more neighbors to visit. So 3, I've already been to all of 3's neighbors, so I don't need to visit anything else here. And the code here is a little simpler, it's a little shorter because I don't need to create a new queue or a new data structure as I'm using recursion. So I start at a source node, and from there, I loop through the neighbors and recurse each time I see an unvisited neighbor. So the order of this is a little different from the BFS order. Does anyone have any questions?
Yeah, I have a question. If we go back one slide, you're describing reverse search, and then we went to 1 and 3 and then 4. But we also said that a graph can be bidirectional, so you can go both ways. What prevents us from going from 3 to 2?
Yeah, so that's why we have to have this extra data structure to keep track of what nodes have been visited. So this could just be an array. So an Boolean array of here size 4, because I have 4 nodes, and I would mark it all as false. And every time I visit a node, I would mark that index as true.
Copy that.
Yeah, so then I would check before I visit a neighbor or put it in my queue if it's already been visited. And if not, then I would put it in, otherwise I wouldn't do anything. And this concept applies to DFS too. So here you also need some way of tracking if your nodes have been visited or not. So you could use the same array, and then whenever you visit it, you would just update your array. All right, so I'm gonna take the remaining time and go through a sample problem together. So this might be a little hard to understand. I'll do my best to explain and see if you have any questions. So the task is that we're given an array, which represents an image where each position in the array represents a pixel. So for example, I have a picture here, which just has black and red pixels. And if this was translated to an array, I could have a 4x4 array where the outside pixels are all black and the inside pixels are all red. And there's going to be an input also that's a pixel location. So in this example, it's the one I have a square around at position 1, 1. And what I want to do is I want to change all adjacent pixels that are of the same color to a new color. So let's say my new color is purple. I want to change all adjacent pixels from the one I selected. So all that are red, that are the same color to purple. So basically I want to replace all the red pixels with purple. And this is called flood fill because in a lot of image editing software, you can, you have a tool where basically you can pick a color and then click on a pixel and then it'll change that pixel and all its surrounding pixels of the same color to your new color. Does anyone have questions about what this problem is trying to solve? Did that make sense? Give me a thumbs up if that made sense.
As a clarifying question, if I were to pick a black, then I would make every black pixel into a purple, right?
Yeah. And then if, let's say I had a separate red square on the right-hand side, and I was changing red, the second square wouldn't change because it doesn't touch the first square. So I only want to care about things that are changing when they touch each other. Okay, so my question is, how is this a graph? Looks like I just have an array. Anyone have ideas of how you could use a graph to represent this? What would the nodes be? What would the edges be? Yeah, Dario?
Can we use the row and the column to represent a connection? So 1, 1 is the starting one, but 1, 2 is the connection, is a neighbor, and 2, 0, 2, 1 will also be a connection, and so on and so forth.
Yeah, that's exactly it. So essentially, I want every array index to be a node. So in this example, I have 16 nodes because there's 4x4 indices. And I'll say a path exists between all horizontal and vertical neighbors. The graph is unweighted, so the edges don't have a weight. And I have a source node, which is my given pixel. So here 1, 1 is my source node. And I'm trying to find all neighbors of the source node with the same color. if this part makes sense, give me a thumbs up. Or if you have questions, shoot them at me. Okay, awesome, cool. So let's work on getting this in code. So if I have my array in code, it would look just like this. I'll just have a bunch of B's and R's in a 2D array. And this is my pseudocode from before, but I've kind of changed it to represent what my problem is asking. So instead of an abstract G of a graph, I'm gonna pass in my array. And instead of something being visited or not visited, what I care about is the color. So if I've already updated a node's color, I'll change it to purple. And that's how I know it's been done and I don't need to do it again. And then when I visit something, if it's still the source color, if it's still red, that's when I know I would have to recurse to it. So, sorry, I have an IDE here. So I hope we can actually write this out as code together. It's a bit bigger. Okay, so I have defined my array and then I copied over my pseudocode where I want to mark some nodes as purple when they change color. And the ones I want to mark is the ones that are the same color as my source node, which I know was red. And in the end, I'm going to print out the new array. So right now I just ran this and it printed the same array, but after I complete writing the code, I hope that the R's can become P's for purple. So let's try and write this in actual Python syntax. So let's make a function dfs, which takes in my array, and I need the current node. But the current node is really just a set of coordinates x and y. So we can pass in x and y to represent where we currently are in the graph. So that's my function definition. We want to mark my current node I visit as purple. So let's say I have x and y is the node I'm visiting. I would set this to P, which is the new color. Let me just put this in a variable. New color equals P, then I can set it. And then I want to check all the neighbors. And if the neighbor was the original color, we're going to recurse to that neighbor. So I think this part is the tricky part here. How do I know what's a neighbor of my x and y coordinate? So Jam says we could have two arrays of 1, 0, -1, 0. Can you explain that a bit more? What are these numbers?
Yeah, so I was thinking that like we want to find the adjacent cells, and that would either be up or down or left or right.
Yeah, that's perfectly right. So I'm just going to copy and paste what you wrote here into my editor.
The first cell, yeah, so like.
So I guess R here is row and C is column. Is that right?
Yes.
Okay, so I think what you're saying here is that we can go through these two arrays and we'll move column and row by these amounts. So for example, I would look for the row that is 1 under for the first time, and then the second iteration, I would look for the column that is 1 over, and then I'll look for the one row that's 1 above, and then the column that's 1 to the left. So this works. I think a more verbose way of kind of saying the same thing is I would basically have some row and column coordinates, and I want to do something like this. So x minus 1 y, x plus 1 of y, and then x and y minus 1, x and y plus 1. And those are the 4 locations I want to check. So this is a little more verbose way of saying the same thing. I'll keep it verbose just for ease of understanding, but John, you're absolutely right that this would work. Okay, so these are the 4 neighbors. And what I want to check is if the neighbor is red or my original color, I'm gonna run DFS on it. So let me make these into if statements. So if it was red, I would run DFS on the graph and the neighbor. So x minus 1, neighbor 1. Okay, so I think I've written out all my pseudocode. I checked all the neighbors. I check if they're red, and if they're red, I'm gonna recurse. Cool. Let me
Question
get
from
rid of those
Dario?
comments. Yeah.
I was just wondering, I'm not like super familiar with Python, but if you try to access an element that is like out of bound in an array, would it give you an error or would it just allow you to do it like in JavaScript?
It would give you an error. So that's a great observation. So that's what this is missing. So we have to check that this index is not out of bounds. So good catch. Let me add that right now. So we have to remember to check that the index is not out of bounds. All right, so here I need to check that x minus 1 is at least 0. If it's negative, we can't access a negative row in the array. And then here, I want to check that x plus 1 is less than the length of the array. That's how many rows there are. And my y minus 1 similarly cannot be negative. And y plus 1 has to be less than the number of columns in my array. Cool, so I think that will solve all my out of bounds errors. Does anyone have questions about this function so far?
I think line 20, it should be len r, right? What is why is it len r of 0?
Oh, here, right? This is what you're asking?
Yes, yes.
Okay, so in my example, my array is a perfect square, so it doesn't matter. But if it wasn't a square, let's say it was 5 by 4, then I want the 5 side and the 4 side.
Oh, okay, yeah, I see.
Yeah, good question. Any other questions? Okay, cool. So let me generalize this a little. So I don't want to hard code the red. So I'm going to say this is the source color, what it used to be, instead of hard coding it as red. So we can run this on both the red and the black parts of my image. All right, so then all that's left is I have to actually call my function. So in here, let's see, what do I want to do? I want to set all nodes as unvisited here. Since I'm just working with the concept of colors, I don't really need to do that. But I need to set the source color. So my source color, let's say, let me move my definition of new color here so we can see this together. And I'll need a starting X and a starting Y. So in my example, it was 1, 1, that was my index. So my source color is going to be my array at that index. That's the source color. So here right now, this would be an R. And then I think that's all the information I need to actually call my function. So I can call my function on my array and then my, let's say, starting X and my starting Y. So let me just rename this to start X and start Y. And I can print out my results after. So let me try running this and see what happens. Awesome, so you can see here that all the R's have been replaced with P's. Let me try this where I replace the black instead of the red. So I'll start at 0, 0 because I know 0, 0 is black. So let's make this 0, 0. This will set the source color automatically to black instead of red. And if all my bounds checking was correct, this shouldn't crash. So let's try running it. And yeah, this looks good to me as well. Now the outside is purple and the inside is red. Any questions?
Hey, I'm a little bit confused on like the visited part. Did you make a visited array or?
So this doesn't really have the concept of visited because I don't want to visit every single node in the graph. So here, what I want to visit is only nodes of the same color. So I can say that my visited is when I set a node to a new color, I've already been there and I don't need to go there again. So that's where I have this here is the same as saying I've already been to array XY. And I know that because I painted it a new color, so I've already been there. So what's unvisited, what do I still have to visit? That's what my if statements are checking. So I only want to visit something that's the original color. So here the concept is that new color represents nodes I already visited. And then the source color represents those I want to use. Yeah, so yeah, exactly. So visit is embedded in my colors. Any other questions? Okay, cool. Okay, let me go back to my slides then. Okay, so I copied and pasted essentially what I wrote into the slides. So when you guys get the slides, you can see this. And if there's any confusion, you can step through this line by line. And then the last thing I wanted to mention was that there's a bunch of common questions associated with graphs. And I tried to find an example for each. These are all links to lead code problems that you can try. So really common is, does a node exist within a graph? Is there a path between two nodes? Does a graph have a cycle? How many connected components are in a graph? And what's the shortest path between the two nodes? So the first 4 of these are all applications of DFS or BFS. But the last question, you'll actually have to use a new algorithm we didn't cover today because of time. It's called Dijkstra's, but it's a well-known algorithm for finding the shortest path between two nodes. So if you're interested in that, you can follow this link and read up on it yourself. And then one other thing we didn't get to cover today is a different way of storing a graph. So we talked about using a 2D array. Another alternative is something called an adjacency list. And again, you can read this when you have time, if you haven't heard of it before. Cool, that's all I have to say about graphs. Anyone have any questions overall?
I'm curious if it's more common to get a question where you need to apply DFS versus BFS.
So usually you can use both approaches to solve either like any question that requires traversals, because that's what they do. The exception is the tree traversals. Jaren talked about the in order, pre-order, and post-order. Those are definitely easier with DFS. But I would say like 90% of the time you can just use what you're more comfortable with.
So which is, let's see, I guess which is more suitable for finding the shortest path, DFS or BFS?
Okay, so that one I said, that's the one that you can't just use BFS or DFS to solve, because all BFS and DFS does is it traverses through your graph. So it just visits nodes for you, but it doesn't keep track of the shortest path.
Okay.
Yeah, a little bit of homework to look up Dijkstra's algorithm.
Do we have any other questions? If not, since we have a little bit of time, just want to kind of like turn into like a bit of a career conversation with Jern and Joyce. This is definitely the favorite part of my the session, which is like asking you guys about things like, hey, like how did you get into computer science in the first place, and what was your process like also preparing for like job interviews, because that's a very intimidating part of the process of trying to become a software engineer. So you guys have like any kind of like experiences that you guys want to share, or like some kind of insight, that would be highly appreciated, both for the fellows and myself even. So
I guess I can start. When I graduated from college, I think a big part of how I got my first job was through internships. So, I attended University of Maryland, College Park. I'm originally from right outside of that area. And I studied computer engineering at University of Maryland. My first introduction to computer science came in a high school class where my teacher did not know computer science. He was a math teacher that they borrowed for a semester to teach comp sci. Luckily, it was not AP computer science, because we probably all would have failed. But it was a good way for me to just like play around and learn. We actually learned in Visual Basic. But it was him not having the background was probably the best thing for us, because we got to learn from each other. We got to explore, and it fostered that love for me for computer science. And so I studied computer engineering, started at Tulane, University of New Orleans, and transferred to Maryland. And then I had internships every summer. So while you guys, I know you all are sort of finishing up your career, but if you can, get on-campus jobs or get an internship if you can, because that was how I got my first job out of college. Was I did study algorithms. I was poring over, spending time with my TAs, poring over, especially like algorithmic problems. But really, what it boiled down to was a recommendation from a company that I interned with, Booz Allen Hamilton, which is a defense contractor. And that started my career. So for my first few years outside of college, I was a software engineer, working on data exchange between intelligence agencies. I was like transforming data to make sure that, when one agency said person and another agency said subject, that we could exchange data and we knew what the other agency meant and could parse that information. And then in 2019, I was so bored to tears of that job that I attended this program called the Recurse Center. So it's sort of like a boot camp, but for folks who already know how to code. And it was an opportunity for me to learn from other people who like programmed light shows and did algorithmic dance raves and had computer science applications for things that I had never even heard about, but were so cool. And that reinvigorated my love of programming. And then I got my job at Greenhouse in 2019. So that period, I had already had a professional job, and going from Recurse to my first job at Greenhouse would put me in the same position you guys are probably in right now of reading, cracking the coding interview, going back through algorithmic problems, doing mock interview with other people that I had attended the Recurse Center with, and just making sure that I was refreshed and knew all the stuff that you guys are learning now, and knowing those things like the back of my hand. And so I'll say, I totally understand what you guys are going through. And it is at any point in your career, it's sort of good to refresh that stuff, even if you're not using it every day. And then I've been at Greenhouse for 2 years. So that was a long-winded, like little traversal through my career.
yeah, well, thank you for sharing that. It's really cool that your career is also dynamic in a sense that you had joined this like defense contractor company and was doing like all kinds of cool stuff, but then eventually realized that, hey, you want to like do something else, and even in the middle of your career you decided like picking up cracking the coding interview and starting all over again, and just kind of rekindling that with love for computer science is a fascinating story to hear. So Yeah, thanks for sharing that. And Joyce, how about you?
Yeah, I think I'm a little similar in that my career has not been super straight line either. I studied computer science and linguistics in school, and I have like a passion for language acquisition. I've always wanted to be a teacher as a kid, so I actually took 2 years off school to teach English in South Korea. And I super loved it, and I was like, this is what I want to do. And then I came back home and I realized the teaching market in my city kind of sucked. Lots of new grad teachers couldn't get jobs because of oversaturated. There was a lot of seniority based issues where you would start off just teaching maybe 1 day a week, if that, and you just have to sit by your phone and pick up the phone if someone's like, hey, I need a supply teacher for the day. So it wasn't ideal. So I was like, what else can I do based on what I'm studying? And I was like, well, I guess I could try the CS route and see how it goes. And all my friends were getting internships at that time. And like at first I was like, I don't know if this is something I'm very interested in, because even though I learned about programming in school, I don't know what being a software engineer is like. And I knew nothing about industry. But basically I just kind of followed my friends, applied for jobs, got my first internship as a backend engineer in Toronto. And I ended up enjoying it a lot more than I thought. I liked kind of like the real application of feeling I'm actually like doing something. And I like the problems I was working with day to day. So then I gave up on my teacher dreams and was set on being a software engineer. So in my senior year, I applied to jobs all over, all types of positions. I didn't like have a strong sense of whether I wanted to work in a certain part of the stack. I didn't have a sense of what type of companies I wanted to work for. But I knew I wanted to leave Toronto because I hate winter. So I was like, I'm gonna move to the West Coast where it doesn't snow. And that's where I targeted my applications. And that was super stressful. I probably applied to like 100 jobs, maybe got like 20 interviews and only passed a couple of those, but luckily one of those was Google, so I moved to the Bay Area. And then eventually I ended up leaving Google because I really wanted to work in a startup and experience a rapidly growing company building a product that was still being developed instead of being very well known.
Yeah, thank you for sharing your experience as well. I actually did not know prior to hearing the story that you were thinking about going to teaching, and now you're like this, like really. I mean, just even looking at like live coding, I'm like, wow, just you're coding that up really fast, right? It's like, so it's like really fantastic to see that. Yeah, you have also kind of decided to make that career like choice in the middle of your career. Like didn't know that you're gonna be a software engineer from the beginning. Yeah, yet you still kind of like made the switch. And yeah, as you said, must have been really stressful, right? Like applying to hundreds of jobs, but all it took was like that one yes that really got you, get started in this field. So yeah, also fascinating here. Yeah, anybody else have questions for those wonderful mentors who led the lesson today? All right. If not, we'll just probably just wrap up the lesson here. But once again, thank you guys so much for volunteering with us and leading this lesson for today. Graphs and trees are definitely not an easy topic. So, and you guys did a fantastic job explaining them in a really clear way. And for the fellows out there, it is a hard topic. So don't be afraid to kind of like follow up and like review the lessons. And also keep practicing it, both with like a mentor or your, fellows in the program, and yeah, or even friends that you have at school. So, but yeah, just make sure you keep up the practice. But with that, we're gonna wrap up our lesson today, and we'll see you guys next week.
Thanks for attending, everyone. Thanks for having us.
Thank you. Goodbye.
Thank you so much. Bye.